Okay, so welcome everyone to the sixth lecture of CPH 290. So today it's a great pleasure to have one of the leaders in the medical AI field, Pranav Rajpurkar. So Pranav is an assistant professor at Harvard University with the Department of Biomedical Informatics. He's also a co-founder of A to Z Radiology AI, which I hope he will talk about a little bit today. Pranav's research focuses on developing AI systems that can interpret medical data, reason through complex problems, and communicate at an expert level with the goal of creating AI doctors that can work independently or alongside human physicians. And he has been recognized with numerous awards, including the Forbes 30 Under 30 in Science, MIT Tech Review's Innovator Under 35, and Google Research Scholar Award. So, Pranav, thank you so much for joining us today, and I'll hand it over to you.
Thank you so much for having me. Can you see my screen as well?
Yes, we can.
Well, delighted to be here. I wish I could be there in person. I found a photo of from 12 years ago of the big game, and certainly look forward to an exciting one this year. But as I was thinking about what I might share with this group here, I thought I'd break it down into two questions. One is, how can we develop AI systems that can match the diagnostic capabilities of medical experts? And then part two is, if we have these systems, how can we use them to truly augment expert capabilities? And the version of the world we're working towards, in my mind, looks a little bit like this, where we have hopefully a cute robot joining in the search for disease, such that we work towards a setup in which we can truly detect everything that there is to be detected. Earlier this year, we put out this review that tried to consolidate efforts towards running trials for AI in medicine to try to understand what was the state of clinical evidence here. And this is the map of 84 trials. And you can see, one, that there's a worldwide distribution, certainly with the US and China having the most number of trials. And there is a large chunk of that being led by gastroenterology, followed by radiology, and then cardiology with a long tail in terms of the specialties involved. One of the interesting setups of these trials is to measure what is the performance of the unassisted clinician versus the AI-assisted clinician. And a lot of these trials report a favorable result with about 81% of 86, trials that have happened so far. And if you look at the constituency of the kind of data that these AI models are being applied to, we'll see that a large chunk of them are applications on medical image or video data. And it's been a natural fit for where AI does really well. And the goal here has been, how can we reduce the burden, the error, and the time associated with the interpretation? There are about three functions which AI serves in the interpretation of medical images today. The first is triage, in which something that is abnormal can be brought to the top of a human's work list. Something that does detection and the localization of abnormalities, and another function of actually being able to quantify after localizing these abnormalities, as is commonly necessary for things like breast lesion characterization. So what I thought we should spend some time talking about first is the progress. And one way in which I divide my thinking is we've made progress on algorithms, data sets, and on human AI interfaces. So starting with algorithms, it was about 2017 or so when the first wave of AI algorithms were shown to work at the level of expertise as clinicians. In the world of radiology, one of the studies I was involved in leading was looking at our ability to train AI models that could detect pathologies from chest X-rays at the level of expert radiologists. Similarly, one of the algorithms we built in 2019 had to do with looking at these single lead electrocardiograms and being able to identify abnormal heart rhythms at the level of cardiologists. And I think one of the main contributions of such studies is to establish the feasibility for real-world deployments. For instance, our algorithm to look at chest X-rays, we built a prototype for as a mobile app where you could take a picture of a chest X-ray from the phone and get diagnoses within seconds. One of the groups working out of Vietnam translated this tool into something that was applied on real patients in Vietnam during COVID. The algorithm we developed to look at abnormal heart rhythms got translated into a FDA-cleared product that is deployed by this company called iRhythm. But in many ways, we're still in the early stages. If you think about tasks where the feasibility is not established, an example of these kind of tasks is comparison tasks. So if you wanted an AI model to look at the sequence of scans and be able to determine that there was an ischemic stroke with a hemorrhagic transformation, there's still not models that can do that very confidently, certainly commercially today. One of the main areas of work in my group has been on self-supervised learning, where the goal is, can we apply algorithms on large swaths of unlabeled data to be able to learn something useful in terms of a representation, which can then serve as a starting point for a supervised learning problem. And this has been a fruitful area of research. I want to share one example from our group. This was the CheckZero algorithm, where the idea was, could we learn from pairs of images and associated clinical reports, which are written at the time of interpretation? And the algorithm was fairly simple. It would learn to encode images and encode reports such that if a report matched an image, then they would be represented similarly in embedding space. And if they didn't match each other, they should be represented differently in embedding space. And using the simple contrastive learning approach, what we can do is learn this model. And the way we apply this model is at inference time for a new image, we can compare the encoding of that image with the encoding of two prompts, one that has the name of the pathology and the other one that has no appended to it. And we see which one of them matches the image better. Simple idea, turns out to be quite effective. And the key result was that we showed that the performance was comparable to radiologist performance on these common chest pathologies. We've recently extended this since 2022, where a recent study with 227 radiologists on the task of detecting 79 pathologies on chest X-rays shows that self-supervised learning actually does well, not just on the common pathologies, but also on the uncommon one. Here, we have divided the 79 pathologies into low prevalence, medium prevalence, and high prevalence, where even for high prevalence, that's still smaller than 10%. And what we see is that both experts and AI have a decrease in performance as we're going to smaller and smaller level of prevalences. But perhaps surprisingly, we can see that the AI model is maintaining, if not increasing, its gap to the expert level performance on average. On the data front, there have been advances that have been just as helpful as the algorithms, sometimes enabling the algorithms themselves to advance. An example of this is the CheckSpread data set, which we made publicly available in 2019, which have led to some works to help us understand how we build optimally self-supervised learning algorithms or build transfer learning algorithms that can learn from natural image data and be applied to medical image data, as well as how we think about learning to defer to experts or uncertainty quantification as it relates to these algorithms. But it's not just the advancement of the algorithms that datasets have enabled. We have also been able to explore what generalization gaps can look like, whether that's being able to play with what happens when we have different training sets used and their relationships to underperformance in ethnic categories or in different sexes, or what happens when we train on one hospital and apply the model on another hospital. And I think the generalization challenge still remains one of the most important problems for medical AI. And here, there are efforts needed on the front of transparency, of post-deployment monitoring, and of clinician AI collaboration to be able to overcome these challenges. One of the ways that we thought about the problem in 2021 was a colleague and I thought, what would happen if we went to hospitals and asked them for a small number of examples from their hospitals, and then combined all that data together to create a big data set. And so kicked off the MIDA initiative, the Medical AI Data for All initiative, with the goal of getting the data from these silos into the hands of AI practitioners, where we capture the diversity in the demographics, equipment, clinical practices. And then before making this available to the public, we think deeply about the design of the task and the annotation procedure such that these are machine learning ready data sets. And so we've now established a workflow by which we approach hospitals and then provide them with the framework that includes both the framework of getting ethics approval from their institution, as well as technical resources to help them with de-identification and transmission. And over the last 3 years, this has now been an effort that's been expanded to about 94 hospitals and counting. We hope to make these data sets available, the first of them, by early next year, and hope that many more groups take the efforts to be able to work on the curation of data sets. On human AI interfaces, the interest that I've had has been how we stop thinking about the comparison of models to clinicians, and how we start thinking about the performance of clinicians when they're assisted by a model versus when they're not. And in many ways, this is the more important question when thinking about deployment. One of the ways in which we can measure the performance with and without this assistance is in the form of a crossover design study, where we have a group of clinicians read the same cases with and without assistance, with a washout period separating those two setups. This is a case in which we had an algorithm detect these abnormal aneurysms, which are ballooning in the blood vessels of the brain, where when they got algorithm assistance, they saw the images on the right, and when they didn't have algorithm assistance, they saw the images as they typically would. And we showed that with this assistance or augmentation, we were able to increase the sensitivity and specificity of the group as a whole. But the interest at that point was not in thinking about just how the average changes, but what happens in the performance differences of individual clinicians. And I'll just have our attention go to panel C, with the box in red, where you can see that one of the radiologists who had the worst performance without augmentation actually has the greatest increase in performance as a result of augmentation, while the other radiologist who had the best performance without augmentation actually has the smallest improvement. In this case, almost no improvement in their performance. But maybe we should be happy that they don't have a drop in performance as a result of augmentation. So that got us thinking about whether we can identify trends in who benefits as a result of AI. One of the big challenges with this study was that in a lot of settings, we care about clinical information that's available at the time of interpretation, which we didn't have in this study. So we ran another study, this time focused on having clinical information available to the clinician and to the model at the time of interpretation. And we had a similar setup where we're, for some of the cases, doing assistance, some of the cases not doing assistance. And our results in this setup were quite interesting. One of the things that we did here was we had the output of the model be both in a form of a heat map over the image, as well as the prediction, in this case of TB, from very unlikely to very likely. And one of the ways in which we made sure this experiment would be trustworthy is we started with training cases. So in training cases for about 100 or so samples, the clinicians get to see the right answer after they make the determination using the AI output. And that way they can calibrate how often they're right versus how often the AI is right. What we found was that the performance of the clinicians improved when they used AI, but that if they had never interfered with the output of the AI, that would have been optimal, with the AI alone performing at 0.79 accuracy. You can see there's a difference in the weightage of sensitivity and specificity here. So we have the algorithm being more specific while being less sensitive, and whether or not that's a good idea is often dependent on the clinical situation that we're in. But what was interesting to us at the time was what happens with the performance of individual clinicians. And what we saw in this case was that while some clinicians had a big improvement in performance as a result of assistance, a lot of clinicians actually had a decrease in performance as a result of assistance, and it wasn't clear why this was the case. So began a multi-year quest to understand the factors that affect human-AI collaboration. In this large-scale study, we involved 227 radiologists, and we aimed to understand the factors affecting the human-AI collaboration success. We started with the output of a model that we saw was better than 78% of the radiologists. And this is a distribution of the radiologists' overall performances along with the algorithm plotted. And then this is a result showing that on average, the performance of the clinicians does not improve as a result of either using AI. It improves when they have clinical history, but not when they have both clinical history and AI outputs. All this to ask the question, well, what affects the success of the collaboration, or why are radiologists not benefiting? And what we identified is that they exhibit automation neglect, which is the idea that you underweight the AI prediction relative to your own. This is the opposite of automation bias, which is often talked about a lot more, where it's the opposite, where you would be weighting the AI a lot more than you should. This turns out not to be what's exhibited here. And the second finding was that providing AI when the AI is certain helps, but when the AI is not certain, actually hurts the performance of the clinicians. One of the curiosities at this point was, is it possible to predict who's going to benefit and who's going to be harmed? And so we published this study in Nature Medicine asking exactly that question. And we found that we see no evidence that we can predict who's going to benefit. If you look at things like years of experience, the specialty in thoracic radiology, or the experience with AI tools, there doesn't seem to be a correlation or an effect between these and the outcome. So what I hope that this section shares is the idea that just because we have expert level AI, we're going to improve clinician performance in a workflow is from our studies rather misguided. And we think it's important to look at experience levels, interaction, case difficulty, and automation bias before we're able to make this jump from one to the other. So that's a little bit about the last 5 years. What I wanted to spend some time on is what will the next 5 years look like, and our bet for that. I think one of the main challenges with medical AI today is that we're in the age of narrow specialized solutions. That means we have algorithms that can do small things really well, like detect a certain abnormality from a certain kind of image. But when we think about what doctors do in terms of how comprehensive they are, how context-driven they are, I'd say the space of tasks that are covered well is rather small. We have narrow AI that does really well for certain tasks, but my interest is in how we think about the gap there and trying to fill that gap and also go beyond what we expect from medical practice today in terms of being able to make predictions about risk, in terms of being able to make suggestions about treatment that are grounded in the data that we see. The vision for generalist medical AI is for AI models that can tackle the full spectrum of tasks that doctors can do and more. And when we started working on this 2 years ago, we thought about making it clear what are the capabilities that would be required for something to be called a generalist medical AI. And we came up with the following: dynamic task specification, which I'll define on the next slide, multimodal inputs and outputs. If we think about what we expect from AI models today, if they've been trained on a particular task and they see a new input, they make the prediction that they've been trained to make. But the vision for the GMAI is to be able to dynamically, once trained, respond to queries like you see with an answer like you see. With multimodal inputs, it's clear that there is vast untapped opportunity in combining different sources of information to be able to make a comprehensive prediction. In this case, that of a diagnosis of rheumatoid arthritis. There are a lot of areas within medicine where it's clear that going multimodal has significant opportunities and significant data modalities from which to pursue those opportunities. With multimodal outputs, the idea is what happens on the other end of the model, where we're interested in building systems that can communicate in natural language, but also have grounding associated with that language, where in this case, we're able to point to the clip of the echo that shows the reduced ejection fraction. We have attempted a prototype of a generalist medical AI for imaging, and this is called the MedVersa model. And I just want to share with you some of the capabilities of MedVersa that we developed. MedVersa is a single model capable of doing a variety of tasks on different modalities. We asked the question, could we have a model that can look at radiographs, dermoscopy images, CT, reports themselves, and perform tasks, including a report generation, VQA, region captioning, classification of skin conditions, segmentations of various lesions or organs. And in order to do this, we developed a custom AI architecture where the key idea is to have the large language model serve as a trainable multimodal orchestrator, deciding when to use modules to be able to do things like segmentations, otherwise be able to output in natural language. The main curiosity, the main hypothesis was whether one generalist model can beat individual specialist models on these tasks and demonstrate at the same time the three key capabilities that define a generalist medical AI. What we showed was that on 9 out of 11 tasks, we had Medversa achieve the state-of-the-art performance on common benchmarks. This includes benchmarks for which we are trying to generate natural language from images, including image captioning, longitudinal captioning, region captioning. It also includes things for which we're interested in classification, like image classification of skin lesions, and also looking at computer vision tasks of object detection, for which we're interested in things like intersection over union with the ground truth. And you can see on the right the number of instances that were used to train this model and the number of images distributed across several key modalities. So I want to show you a demo of Medversa. So we're going to start with a chest X-ray interpretation where we can use a prompt like characterize the findings, have the model come up with the findings in natural language. This model is not only capable of looking at the image, but it also takes into account the context that you see on top. So on another case here, it's able to make the determination, among other things, of moderate pulmonary edema. So the model should be consistent. If I say how severe is the pulmonary edema, it should be able to say moderate and be consistent with its output. We can say things that are going to require segmentation, in this case of the heart. Not quite right, but I like to say its heart's in the right place. We can now look at skin images, be able to make diagnoses off of those, look at CTs in this case, and be able to perform tasks like segmentation of the liver or segmentation of the pancreas. And it's very exciting that we can have a single model be capable of all these different tasks. So this is a research use tool that we're very interested in seeing how we can make it as helpful as possible. One of the questions that I've been interested in is whether or not it's clear that these models are at the level of expertise of, well, experts. And so one way we set up this study is to say, if we gave an expert 2 reports, one of them generated by the model, another generated by an expert, can they distinguish which one is which one is better? And with this setup, we saw that expert-written reports are still preferred. And the reason for this is on abnormal cases, often the humans are able to catch findings that were potentially missed or potentially overcalled by the AI model. While on normal cases, you can see they're pretty much equivalent at this point. I expect this graph will change significantly as models evolve over the upcoming year or two. We developed a benchmark to be able to track progress on this task. Our benchmark is called RexRank, and currently Medversa is the best benchmark model on the task of generating reports from chest radiographs. One of the opportunities this opens is the ability to modify draft reports written by AI and finalize them. And one of the interests here is in understanding, does this save time for the expert? Does this reduce the mental effort? Does this increase their confidence in reporting? And we're starting with small studies here, but we have preliminary data to show that we can indeed save time, mental effort, and increase confidence as a result of using the AI output. It's once again clear that there is variability between different experts, and so we need to think about how to make the solution really work across different experts. Going beyond how things affect experts, one of the interests that we have in the group is how we think about delivery directly to patients. Here, the vision for the generalist model is to be able to have these customized interactive reports for different levels of expertise. One key problem we're interested in is how we make these radiology reports understandable to patients. The common experience, certainly as true in the US as it is in many parts of the world, is often after someone gets a scan, they get a disc on which they have the scan and a report that is generated and often sent over email. However, this radiology reports are very hard often to understand by lay people and very hard to be able to connect with what's seen on the image, which is on your disc. So the idea that we're interested in is making it very clear what every line in the report is talking about, both by pointing to the part of the scan and pointing to anatomy in the human body. So we prototyped this setup where we would be able to explain each one of these findings compared to what a normal image for an age-matched control would look like, what the organ looks like, and having a virtual avatar explain these findings. We both developed tools and used existing tools to be able to do this. I want to show you a demo of what we're able to do here. So in this particular case, we're looking at the explanation for aortic calcifications, and the virtual avatar is talking through the finding, explaining it in natural language. Soon, we'll see a comparison being made to a reference normal image, which doesn't have any aortic calcifications. And then we move to a new finding, this one of osteophytes, and we're able to once again explain this in natural language and then compare it with what's going on in the reference normal image. This is still a very early prototype, but one that goes to show this vision for having direct-to-patient delivery. So, I've covered a lot of stuff that was, done by very smart people in my lab. And so these are some of the people contributing to these studies. Professor Alla also asked me to talk about some of our efforts towards translating AI tools from medicine into things that work directly as products. And as an effort towards that, I want to share some of what we've been doing in the commercial space. One of my interests has been in how we are able to interpret abdomen pelvis CT. And towards this front, co-founded a company earlier this year called A to Z Radiology AI. And the first product, which is a research use product, is about how we do abdomen pelvis CT interpretation, where we have shown that this model is able to achieve a high AUC across 21 clinically useful findings, where our validation is done on data from 2 health systems that are not part of training. One of the interests here is in being able to capture acute and chronic abdomen and pelvis conditions, which often span various organ systems and potential medical emergencies. One of our efforts on this front has been how do we make sure that the model can work across different subgroups And one of the analyses that we've been doing and interested in leading the front on is how algorithms can work across different patient subgroups and also across different imaging equipment and any other variable that might affect the performance of the algorithm. We're able to show so far that this first model, A to Z1, is able to maintain high performance across both the subgroups as well as practices in different US states. One of the challenges that often face algorithms is how one thinks about operating thresholds. And one of the decisions we've made is to have the outputs of likely, possible, and unlikely, where you can see that when the model calls a particular pathology likely, it's right about it more than half the time. This is important because often in practice, when an alert is created for something that the model deems likely, it's important that there are not too many false positives because of the long history of technologies creating alert fatigue in the context of medicine. Back to the academic side of things, one of the opportunities which I've been very engaged in over the past many years has been boot camps to help students get involved in the space of AI and medicine. It's been scoped to originally Harvard and Stanford with opportunity for doctors all around the world. But perhaps, you know, we bring it to Cal in the near future. And certainly if there's a compelling reason to do so, you can send in an application. So I'll end there. Thank you for having me. I really enjoy talking about this subject and take any opportunity to do so. And delighted to spend some time answering questions.
Thank you so much. Yeah, so Fido has a question.
Great talk.
If you can't hear him, I can repeat the question. I'm not sure about the microphone setup in the room.
So earlier in the talk, you gave the example of one of the radiologists who had the lowest performing score actually improving the most due to the AI assistance. I'm curious, have you thought of using this kind of AI assistance as a way to kind of train or refresh physicians? For example, like maybe improve the baseline of low performing physicians?
I think I heard some of the question. It was quite soft. So Emily, if you're able to repeat it for me, that'd be great.
Yeah, so I mean, you can come closer.
Okay. So earlier in the talk, you gave the example of one of the radiologists, I believe radiologist number 4.
Yeah.
They had the worst performance, but they improved the most. So I'm just curious, have you thought of, or do you see any potential to use these AI tools to perhaps improve baseline performance of physicians? Like, for example, if there's like a low performing physician, could you use this technology to perhaps improve their baseline or refresh them if their scores are deviating from the AI quite a lot?
Yeah, in theory, I think in practice, I think we would need more evidence that you can, in fact, do it in a way that creates trust and also doesn't mislead whoever is the user into something that's faulty and inaccurate. I think it's not so clear to me, at least, that there's a generalizable way of doing this in the current state of things.
So I had a question within the same setup about like model uncertainty. And I saw in one of your slides that the model uncertainty had an effect on the human AI intervention. Can you talk more about that?
Yeah, so we actually have this work that will soon be published, where we have attempted to get at a fine-grained method for also outputting uncertainty associated with the generalist model's output. So, you know, we can do this both at the level of the full output, but also at the level of some fine-grained claims in the output. I think it's a very important part of the communication to the end user. Somehow, I think, you know, ideally, we'd want to end up in a system where we don't have to communicate the uncertainty. This might be a little bit of a contrarian view, but I think the ultimate user interface needs to be as simple as possible. And I think anything that complicates a simple interface also brings with it friction in terms of how well and easily someone's able to use something at an expert level. As a very concrete demonstration of this, when we are using tools like ChatGPT, I think one way in which uncertainty is more or less communicated is sometimes the system comes with two outputs and it says which one of the two is better. Now, I don't know whether that's linked directly to uncertainty, but that seems to me like a nice way of being able to allocate some sort of interface to the problem of uncertainty demonstration. But in most use cases, none of us care about the token probabilities associated with, you know, my general day-to-day use of ChatGPT. Now, it's easy to see why that should be different for medicine, where, you know, probabilities and differentials are very natural part of communicating or certainly thinking about, you know, certain ways of determining the workflow. And, you know, we have very clear risk thresholds, for instance, for determining whether someone should be on, you know, a statin, let's say. So there's certainly a good UI middle ground, UX middle ground to be found when it comes to medical use cases in terms of communicating the uncertainty.
Yeah. Other questions in the room? There are some questions online. Yeah, before reading the online questions, just another point about the generalist AI direction. And I wonder if you think that going more general is actually going to impede translation unless we like, because like medicine is practiced in a very specialized way. Also, probably regulatory clearances would be very specific. So do you think that the value proposition for generalist AI is like knowledge transfer, that you are doing better on individual tasks? Shouldn't this also be reflected in a change in the way we practice medicine? That it's not that the clinician is inputting queries, but the model is also resurfacing things that they would not have asked about that has to do with whole person care, especially with patients who have comorbidities and like multiple things that might not be obvious to the specialists that they are seeing that this is relevant for their diagnosis.
Yeah, I think this is to me both a theoretical question and a practical question. The theoretical hypothesis for me is, would a generalist model be more accurate than a specialist model as we continue to expand the task? And I strongly believe the answer is yes. And there's no question in my mind that that's going to be the case. The more practical question is almost around one, whether or not it would make sense for anyone to truly have access to this data that would be required to have a single model, or whether we end up in a setup where people have specialist models because they don't have a mechanism of centralizing all that data. So that's practical consideration number one. Practical consideration number two is when it comes to the evaluation of more and more generalist setups, I think it becomes less and less clear that they can be thought of as tools, and more shifts towards thinking about certification the way we certify people in terms of their expertise. The way we certify people in terms of their expertise is often these board certifications, right? It's to say, someone's qualified because they're able to take this test and show. But that's often not the only way that we're doing this. Some of the way in which we're doing this is also we have apprenticeship models in practice where for the course of a few years, someone trains under the tutelage or the supervision of someone else who has the license to be able to practice independently. And so I think this idea of having supervised tutelage is, I think, one that eventually needs to be a part of how we think about the validation of these systems over time. And certainly not something we are very ready for today. But I think outside the scope of medicine is something that's very much implemented in terms of aligning models with human preferences in the general use cases.
Thanks. Yeah, we can take some virtual questions. First question is, could you describe a bit how the flow of imaging AI would be probably in terms of time and speed in the augmentation process? I think this is a question about the result that you had about saving time in a workflow. Like maybe you can describe that a little bit more.
Yeah, sure. So in that particular case, the idea was if you have to generate a report as a person, would you be better off starting with a starting point that's been set by the AI? And so that's the way the workflow is set up. And then we have automatic time measures, and then some of the outcomes that we're getting there are self-assessed.
Let's see. Second question. Do you see that future generalist biomedical AIs would need to have an orchestrator module like the LLM module that you presented and use expert modules as... Oh, so I think the general gist of this question, I think I had this question as well. Do you think the generalist AI model, does it have, it seemed like from the model that you presented that there's a lot of inductive biases, that you have like multiple sub-models and you are kind of triaging the inputs according to the input query. Do you think this is the kind of, this is where the models will what the models will converge to, or are we going to have like more unified architectures as well?
I would say it comes down to, again, a practical consideration, which is how much compute do you have?
Yeah.
And I think as a function of how much compute we have, I would say, of course, end-to-end makes sense in the case in which we have infinite compute and infinite data. The problem is that when we think about the constraints that data and compute afford us, then I think often it makes sense to have modules which you can start off in terms of building blocks.
Yeah. Other questions in the room? Okay. I think that's... Oh, there's one more question, virtual. That's like a general question about reproducibility in generative AI. And do you think about it differently than, for instance, the models that respond to queries as opposed to models that are discriminative models that run on like specific inputs, produce specific outputs? There might be variations in queries that kind of undermine reproducibility or generalizability across sites. Is this something that concerns you, or have you thought about this?
Yeah, I mean, I think of it almost on two levels. One is the reproducibility of a output once you have a trained model. And second is the reproducibility of actually being able to retrain that model to get you the same sort of, Same sort of distribution in terms of outputs again. Yeah, I don't know if I have any interesting observations there beyond I guess what's obvious. So no.
Yeah, I think since you're running like actual studies with human users, probably that's the best way to just evaluate the effect of a model in a new system, where maybe the distribution of queries input to the system might be different. I guess
Yeah.
that would be the only way to test that. Okay, so thank you so much, Pranav.
Thank you. Thank you so much for having me.
Great having you. Yeah, and catch up
Cool.
later.
All right. Catch you later. Bye.
Bye.